Thank you for, okay. Thank you for inviting me. So my talk, let me see if I can just do something like that. Okay. So the title of my talk is The Wavefunction Is as the Wavefunction Does. And, okay. So the next thing that I'm gonna, okay. What are we doing? So what I'm gonna do is make a lot of people upset because I'm not a big fan of the wave function at all, in the sense that what I'm going to propose is an account of how to think about the wave function in a way which is not epistemic for those people who do not want to think of the wave function as something material, as a physical thing at all. So basically, if you want to have a slogan about what I'm going to talk about, is a proposal about how you can see the wave function as ontic without thinking of it as material. Okay, so let's try and go back to the question that you pose yourself if you are a scientific realist and you're dealing with quantum theory. So the natural attitude, at least that's what I think is natural, is to think that the wave function is the main object of the theory. That's what you find in the physics books. That's what people are always talking about. So if you want to be a realist about a theory, then what is the variable of the theory that I'm going to be realist about? Well, the wave function. However, there are two problems with that. One is the well-known measurement problem, or the problem with Schrödinger's cat. And the other one is what we can call the configuration space problem, or something like those terms. Okay, so I mean, even if you're all aware of what these problems are, I think it's going to be instructive to discuss them one more time. So here's a very simple way of presenting the first problem, the problem of Schrödinger's cat. So there are these three claims. The wave function provides the complete description of any physical system. The wave function evolves according to the Schrödinger's equation. And when you're making an experiment, you have a definite outcome. So the problem is that if you try to put them all together, they cannot be, because there are macroscopic superpositions that form. And so if you believe that experiments have definite outcomes, macroscopic superposition is just like the opposite of that. So, so what are the solutions? Again, we all know what they are. The pilot wave theory, also known as Bohm mechanics, the Broglie-Bohm theory. Even if I don't want to enter into the debate about whether it's the Broglie or Bohm, I mean, that's not what I'm interested in. We know that such a theory, what it does is that denies that the wave function is complete. Then there is the spontaneous collapse theory, or theories, which basically what they have in common is that the wave function does not evolve according to the Schrödinger equation, but in contrast, it evolves according to a stochastic equation that gives rise to spontaneous localization of the wave function, so that microscopic superposition exists, but macroscopics do not. So the third one is the many-word theory, that basically embraces the idea that macroscopic superpositions are real, and deals with how we can understand them properly and make them, and you know, in virtue of the fact that we don't see them. Okay, so we seem to have found a solution of that, but then we have another problem. All these theories, as we were saying at the beginning, may not have the original problem, may not involve the notion of measurement or observer at the fundamental level, but still they have the problem of the fact that the wave function, as it is straightforwardly interpreted, lives in, is defined in configuration space, which is a highly dimensional space. And so the basic suggestion is that if the wave function is what is real, and the wave function is lives in this high dimensional space, then this space is what is physically real. It's physical space, right? It's the arena in which the phenomena happen. And this is in tension with our experience, that physical state instead is three-dimensional. Okay. So what are the reactions to this problem? The reactions to this problem are basically three. And I'm gonna go through them as quickly as I can to motivate my approach. So one is just to say, well, yeah, sure, it's a problem, but it's not a real problem. We can fix it, we can solve it. The wave function, it makes sense to think of the wave function as a physical field on configuration space. And what we need to do is to extract the three-dimensional world that we perceive from the wave function. This is, in a nutshell, is what wave function realism is all about. It's not the denial that three-dimensional object and three-dimensional space are real. They are real, but they're not fundamental. So the different approaches to wave function realism are approaches to extract these three-dimensional objects from the fundamental world of the wave function in configuration space. And we know that David and Alisa and Jill and others have worked on that from different perspectives. David has worked functionally extracting the three-dimensional microscopic object from the wave function. He talks about shadows. Alisa talks about symmetries to privilege a three-dimensional decomposition of configuration space. And then there are other approaches that involve grounding.
You heard from no one?
And things like that. Okay, so as much as
just want to see what she's doing.
Can you still? Yeah. Okay. Okay. So of course, people may find these approaches interesting and fascinating, but they also have.
We're hearing a little bit of crosstalk. Can everyone just be sure to make sure your microphones are muted? Thanks, everybody. Just double check. Sorry about that, Valia. Go ahead.
Oh, no problem. Thank you for doing that. Okay, so basically what I want to say is that there are challenges to these approaches. For example, I mean, if you want to invoke grounding, you have to spell out exactly what it is, and the metaphysicians in the group know exactly how challenging that is and how many notions of grounding are available. Some other people may object that this kind of approach is extremely revisionary, and all things being equal, other less radical explanations should be preferred. I guess that's what Nina would say. Other people would say that there is a tension in trying to make sense of the wave function in configuration space and make it and make sense of relevant symmetries with that. Some people may be okay with that, but some other people may be, you know, be wanting to preserve as much symmetries as possible. And then others have underlined the notion of empirical incoherence, namely the idea that if your theory is fundamentally based on something which is not fundamentally three-dimensional, then it's going to be difficult to figure out exactly how to confirm the theory. This is what among the people in here probably Tim would say. But regardless of who would say what, there seem like, you know, relevant challenges here that, of course, the wave function realists are aware of, and they provided replies to that. But maybe some of the challenges have been regarded as a reason to change the type of approach into something else. Some people have proposed that this is the second kind of approaches that I'm going to explore. Namely, they say, okay, fine. We don't want a physical field in configuration space. Let's try and see whether we can think of the wave function as a physical field in three-dimensional space instead. Okay, so in this way, we would not have the problem of extracting or notion of emergence and stuff like that. And so this is the approach that has been developed by Davide, by Mario, by Eddie, by Gordon, and taking up an idea from Forrest, that the wave function is actually not a function, but is a multi-field, something which assigns property to a plurality of points rather than a single point in three-dimensional space. This, I mean, again, I don't mean to go too fast over this, but I mean, the point with this is that some people have found it still kind of revisionary. What kind of field is a multi-field? Some other people have focused on the problem that we'd have with symmetries. Another way of approaching to this, which has been implemented by Travis, this theory of exclusively local beables, is to actually work out a different theory in which, instead of having an object such as the wave function, which is naturally interpreted as a configuration space function, we actually substitute that. This has been done in the framework of the de Broglie-Bohm theory. It has been substituting the wave function with a set of three-dimensional field instead. Okay, so the idea is that, however, technically, it's not the simplest and theory that one can have as there are actually infinitely many fields. So if you want to reproduce the exact prediction of quantum theory, you will have to add infinitely many fields. Okay, so another approach to this is just to say, look, just forget about the wave function being a material field, a physical field. Just forget about it. That's not what it is. Okay, that it doesn't represent matter. It doesn't. Okay, it's another kind of thing. And so one way of doing this is to say, look, the wave function is still ontic in the sense that it's objective, but it represents some sort of nomological aspect of the word, right? And the other one, that's a type 1 attempt of trying to deny the materiality of the wave function. And the second attempt is one which I want to discuss anyway, which is, because it's important for my view, is that the wave function is actually epistemic. We just forget about the fact that it's ontic. It doesn't represent anything. It's not anything, something objective, rather represent our knowledge, the knowledge of an observer regarding the theory. Here's one, an elaboration a little bit about what's going on in type 1 attempts. So we have the weak nomological view, according to which the wave function can be thought as a property, and maybe a dispositional property. So the idea is that the wave function doesn't represent matter. It tells matter how to move, as a dispositional property tells matter how to move. It disposes the particle to behave in a particular way. Sorry, I'm characterizing the view kind of too crudely, but you understand what I mean. And here, maybe it's kind of a stretch, but let's say we can just say, okay, so the dispositional property approach, you can see the people over there, Montanes, Suarez, Yao, and maybe other people. Other view that may be characterized as being belonging to this. I mean, if you don't like the name, forget about it. I mean, the point is that the wave function is still something that it's a kind of a property of space-time containing all the relevant dynamical information. This is maybe what David Wallace and Christine Timpson may be characterizing in saying, like, I put them in the weak nomological views. If you disagree, I apologize. Or the third kind of view is invoking some kind of structuralism and say, look, what the wave function is some sort of structure. If you don't like properties, maybe that's one way to go and say, look, it's captured the structure situation of the word. This is what Peter may be saying. So the good things about this approach is that they square better with symmetries, which I didn't really explain why. But the bad things is that, I mean bad, you may want to complain, if you want to complain about something, is that in the first case, properties, dispositional properties, I mean, what are properties? What are dispositional properties? How am I supposed to think about this? Some other people may object that density matrices are the wrong kind of objects because they're non-separable, and that's what Tim would say. And what about the structuralist approach? The structuralist approach, when we say, okay, yeah, I mean, you may call it structure, but still the real question is exactly to understand what that means. So these are kind of, I mean, mysterious concept. They're just hiding the problem. Okay, so the type 1b attempts are the strong nomological views, and I'm borrowing a notation that you find in Eddie's paper, is to say that the wave function is actually a law of nature. You can have, this was been proposed by Dirk Goldstein, Tumulka, Teufel, and Zangi. There are Humean version of Craig, Elizabeth Miller, Michael Asfeld, and as well. And okay, so what about this kind of approaches? Well, I mean, this avoids to think about properties, we already know roughly what we mean by laws, or there is a problem that everyone has with laws. So that's good. What are the bad things? Well, the bad things are that, you know, the wave function is nomological, really, right? I mean, the wave function evolves according to an equation of evolution. We think of the wave function, sorry, we think of laws of nature as being what they are. They are what they are. They don't change with time. So what the heck are you talking about? So that's the complaint that one can raise. In addition, the wave function is not unique, while we think of the laws as being unique. So what's going on? Okay, what about attempts number 2? Okay, so these approaches are epistemic approaches. The wave function represents the knowledge of the system. It doesn't represent anything in the world or anything objective, material or not. You can identify many approaches which one can classify as epistemic. For example, you have pragmatist approaches that are really like that, like the one of Healy, Richard Healy and Carlo Rovelli, or you have information theoretic approaches by Bob Pitowski, you have cubism, you have reinforced realism, I don't mean to enter into details about these approaches, and I don't mean to be exhaustive in presenting them all. The point that I want to make is that what they have in common is they all share this pragmatic component, that the wave function is a tool which allows the theory to explain the phenomena and makes new prediction. That's what it does. Okay, what I regard to be the main problems with this kind of approaches is that one can complain, what about interference? You know, interference is a phenomenon that happens, and how can you explain this phenomenon, which is objective, with some kind of, you know, wave function, which is actually epistemic? Then there are the no-go theorems against epistemic views, and so at least people. I mean, some people, like for example, Bubin-Pitowski, and I'm aware of, are provided responses to this, but that's the challenges that, in general, epistemic approaches will face. Okay, so just to give you a brief overview about this, which is going to be relevant for me, is that here is a bunch of claims that you can read from Healy and from Bubin-Pitowski. What the wave function is something which prescribes our own epistemic attitudes towards claim about physical situation should be. The wave function, what it does, it gives you the probability which prescribe what the experimenter should believe. Okay, so you have a given particular experimental situation. What the wave function gives you is the way in which what you should expect. This is a pragmatic view because it is concerned about the explanation, right? It's not concerned about which, you know, object in the theory is representing which. The wave function is not some entity to reify or materialize. That's what Healy says, rather than it is something which allows the theory to be explanatory. Bubin-Pitowski said that quantum mechanics is fundamentally about measurement outcomes, with statistics are recovered by the constraint that Hilbert space structure imposes on quantum dynamics. The wave function has a role of describing an agent preferences or expectations or degrees of beliefs or something like that about measurement outcomes. Okay, now let's go back to the original question. So suppose you want to be a realist about the wave function. You want to think that the wave function is something ontic, something which is objective, the case. But partially because of the reason that I presented, you don't want to be a materialist about it. You don't want to say it represents something material. It doesn't represent a physical object. Okay, so suppose you're trying to build this ontic non-material view, okay, and you're interested in the question about what the wave function is. So what are your options? Your options are, I mean, either you go ontic non-material and go nomic, but they have problems that we saw, or you go epistemic, right? But I mean, epistemic is not really realist. How can they be real? I mean, this is kind of tricky because, of course, if you've read Bubin-Pitowski, you know that they consider themselves realist. Okay, but keeping that aside, what I want to explore is this view that maybe there is something that epistemic approaches can teach us. And can help us construct a better account of the wave function if you don't want to consider the wave function as material, but you want to be realist in the sense objective about it. So let's see. The nomological view, which in one way or another I think is the main way to go. I mean, the most promising way to go if you want to think of the wave function in this way. Has problems, but if you compare that to the pragmatic view, they seem to agree at least in three things. the wave function lacks a representation role, right? The wave function does represent something material. Okay. They agree on the explanatory role of the wave function. They agree on the idea that the wave function is dispensable from the material ontology of quantum mechanics. Yeah, okay. But you know, that's the problem, right? How do you dispense it with, right? On one hand, you have the no-go theorems. On the other hand, you have time dependence and non-uniqueness. So what are you gonna do? Okay, so I want to bring something else to the table. So think about functionalism. Functionalism has been used so many times in so many areas of philosophy that it will have certainly many meanings. So you see functionalism in the philosophy of mind, but recently you've seen functionalism also in the philosophy of physics. I will take function to mean something like this, that certain entities can be reduced to their functional role. Okay, so this has been explored by Leonard Knox, who have argued that space-time can be functionalized in classical theories of gravity. She wants to say that the entity is spatio-temporal as determined by its functional role. Okay, Laman-Buttrich has said that space-time can be functionalized in quantum gravity. Space-time can emerge if one recovers those features which are functionally relevant in producing observation. And David has functionalized three-dimensional objects in quantum mechanics, as we anticipate. I mean, I mentioned before, earlier, three-dimensional objects are determined by the causal roles, and the wave function dynamically give rise to the empirical and the empirical evidence. Okay, so yes, so this is something that I mentioned before. So what all these things have in common, all these functional approaches, many of these functional approaches seem to have in common is the problem of empirical incoherence that I've been saying before. A theory is empirically incoherent if its truth undermines the empirical justification for believing it. Any theory is confirmed by spatial temporal observation. So, however, if the fundamental entities of a theory, if the fundamental entity of a theory which rejects space-time are as fundamental are known spatial temporal, therefore our observation provide no evidence for the theory in the first place. So the idea is that the theory basically undermines our belief in it. Okay. So finally, let's see what we may learn from all this. My general view is that there are three important components to understand what the wave function is. There is a nomological component. The wave function acts. It's a governing entity, or it's something that tells how the dynamics are supposed to play out. It has a pragmatic component in the sense that it is explanatory. It's just a tool that it is a tool that we use to explain the phenomena. And what I'm going to explore is a functionalist component, namely the wave function is determined. What it is determined by what it does. So in this way, the view would capture, the view that I'm going to explore in the last minutes of the talk, will capture the intuitions of the different approaches. It is the wave functions being a part of the law as a guiding entity, the wave function being explanatory rather than representational, and can be dispensed with without reducing it to a functional role in the theory, by reducing it. So in taking from all these approaches in part, but not in their totality, this new perspective can avoid the objection to each and every one of the single views taken separately. So it's just like, okay, wins everything. So here is a little bit of elaboration. The wave function is not a law of nature, strictly speaking, because of the objections that we said, but it is an ingredient of the law. Okay, so it is one of the ingredients of the law which allow the dynamics of matter to be written down. For example, in Roman mechanics, a wave function can be taken as a force or a potential or something like that. Being merely an ingredient of in the law and not the law itself, the wave function does not have to be unique. Like potentials are not need to be unique, and it can be dispensed with. Other entities such as the density matrix or whatever can play exactly the very same role, and it doesn't have to be time independent. In this way of understanding the nomological view, one avoids the objection of the pure nomological view. Moreover, the wave function as a pragmatic component, it's a useful object to adequately recover the empirical prediction, namely the Born rule. This is what it has in common with Healy's approach. The wave function is not representing anything. It is explanatory. Pragmatic one uses the wave function to generate the probability outcomes given by the Born rule, but one could have chosen another object evolving according to another evolution equation. The fact that the quantum mechanics is formulated in terms of the wave function is contingent to other super empirical considerations such as simplicity and explanatory power. But importantly, in contrast with other epistemic approaches, the wave function has nothing to do with our knowledge of the system. So it's not epistemic, right? So because of this, right, it doesn't fall prey of the no-go theorem, doesn't fall prey of the problem with the interference, explaining interference. The last bit has to do with functionalism in the sense that the wave function is defined by its function in the theory. It is what it does, okay? Of course, this works well in the primitive ontology approach, in which what you have is the primitive ontology is, we can just say, microscopic stuff in three-dimensional space, which represent matter. The scientific image, namely the theory, and the manifest image, namely what we observe, namely the empirical data, meet at the level of the primitive ontology, and the wave function is what it does, namely it is what is needed to be in order to get the empirical data back. Okay, so interestingly to me, this doesn't work only for the primitive ontology approach, but it works for all kinds of approaches that are requiring local beables or which maybe, I mean, perhaps surprisingly to some, this is how I regard epistemic approaches. If you read carefully Boop and Petoskey or even Healy, what they want to say is that they do have local beables. They're simply not microscopics. These local beables, what is matter made of? It doesn't have to be microscopic like the primitive ontology approach. I mean, you can think of local beables, I mean, forgetting about what Bell actually meant with them. But now, if you think about some entity in two-dimensional space that you're looking at, right? You can think the measurement results are such entity, okay? And that's what the information theoretic approach is all about, right? Measurement outcomes. The empirical data are encoded in the measurement outcome, and the wave function is as the wave function does. It is what it needs to be in order to get the empirical data back. It doesn't have to be epistemic, not even in their approach. That's what I'm trying to say. And this would be, you know, good for them, because in that way they would avoid a bunch of problems connected with no-go theorems. They would have still other problems Okay, I'm not necessarily advocating for them. If you know me, I wouldn't. You know that I never would. But in this case, this could be an improvement also for them. You know, there is no problem of empirical coherence because, you know, it's in 3 dimensions. According to functionalism, in order to account for observation, one only has to recover those features which are relevant in producing the data. In this case, what grounds the evidence is not the wave function, but the 3-dimensional thing that you're looking at, the PO, the local variable, whatever. Given that the experimental results are expressed as trajectories of the primitive ontology of local variables, and they are in space-time, so you don't have any empirical problem of empirical incoherence. So the wave function has the functional role of generating the empirical evidence encoded in the 3-dimensional entity that you're considering to be representing what there is. So, okay, so I went a little bit too quick. So here's a summary of what I wanted to say. The wave function has 3 important, distinctive, but connected roles. It is part of the laws of nature, and as such contributes in determining the trajectories of matter. As such, it has an explanatory role in accounting for the experimental results, but it is not representational. Because of this, the wave function can be described in terms of its functional role. The advantages of this approach is that it has a nomological role without the law, so it does not matter whether it is time evolving or unique. It has an explanatory, non-representational role without being epistemic, thereby avoiding the no-go theorem problems. It can be functionalized in the sense that its role in the theory is non-fundamental insofar as it is to govern the motion of matter, therefore bypassing the problem of empirical incoherence. So I have begun to articulate a view in which the wave function is best seen as non-representational, but as an explanatory entity that can be functionalized in virtue of its nomological role. This view figures better than the main alternative view in the which I think is a nomological view, weak or strong. So thank you very much for your attention. Okay.
Okay, so we have a lot of people here. To make sure everyone has a chance to ask questions, please use the hand raising feature. If you're new to Zoom, you want to go down to the ribbon at the bottom of the screen. You'll see a button called Participants. If you click on that button, it'll load up a list of all the participants, and you should see an icon that shows raise hand. I will see your name with your hand raised in the chronological order in which you've raised your hands. So I'll attempt to go in order. Valia, thank you for finishing not just on time, but a little early. That means we'll have more time for questions. So I'm going to start with Alyssa, who has her hand raised. I'll call on you. Please remember when I call on you to click on the hand raise tool to remove your hand. Otherwise, I'll get confused and I won't know whose hand is still raised. So uncheck your hand raising. I see Alyssa's already done that, and then unmute, and then you can ask your question. Thanks, Alyssa. Go for it.
Thanks, Valia. That was like such an awesome overview. And so I guess I just wanted to get clearer on what your view is, because you raised a mysteriousness objection to others. And this is, some of this is new to me. So usually functionalism is like interpreted as a view where something is like nothing over and above something else. So you were always describing it, the functionalist aspect is of your view as wave function is what the wave function does, but like traditionally in philosophy of mind, in functionalism, it would be something more like the wave function is what something else does. It's nothing over and above the behavior of something else. And so I just wasn't clear, is your view like that? Is it you have the primitive ontology and it behaves in a certain way? And the wave function is nothing over and above this behavior in the in the primitive ontology, and maybe the relations between measurements and measurement results or something like that? Or is this like the wave function is really something over and above? So.
Okay, so let me see if I can understand the question. So you want me to be clear about what kind of functionalism is that I'm advocating for?
Yeah, I mean, I think I want to be clear about what your view is in general, because you say like it's a gnomic view, but the wave function's not a law, it's an ingredient in laws. So, I mean, you brought up you know, the view can't be mysterious. And so I feel like I'm not totally clear on what the view is. So I just felt like a way that I could understand it better would be maybe you starting to like just answer this question. Like typically, you know, for functionalists, most like, you know, functionalists that try to articulate functionalism as some kind of reductive physicalism will say like, I'm a functionalist about consciousness, and that I think like consciousness is nothing over and above the behavior of, you know, neurons or, you know, something physical. And so is that your kind of functionalism? Is it that the wave function is nothing over and above the behavior of the primitive ontology or something like that? Or is the wave function something over and above, and it's got this kind of pattern or whatever? I don't know, does that help?
Yes, okay, so yeah, of course, yes, so I see the point. So, so how can I complain someone else being mysterious if I'm not clear about what I'm saying? Okay, so, so no, what I want to say is that we are trying, so it's not going to be probably very satisfactory, because of course this is not something that I have necessarily worked out completely. So this is a workshop. So what I wanted to try and capture is the different intuitions that are guiding everyone, right? So we have this theory, we don't know what to say about it. And so I thought that in this way, we could capture many of the intuition, including the last that you were saying, namely that the wave function plays a particular role. So do I want to say that the wave function reduces to the primitive ontology, or do I want to say something over and above? That's probably going to depend. I mean, as things stand now, the information which is in the wave function cannot be reduced by motion of matter. Okay, so I would have to say that whatever there is in the wave function cannot be, is not present in the information about that we have over there. So functioning therefore cannot be straightforwardly as you presented in the case of the philosophy of mind, and which is something that I need to be clear. Thank you. What I wanted with that to say is that you know, what I liked about functionalism in philosophy is that it has been recognized as a kind of a way of spelling out what something is. Okay, so maybe I shouldn't call it functionalism, because in this way it's kind of confusing, because that's what other people have in mind. So if you guys have a better suggestion of how I should call it, but what I want to say is that it doesn't reduce, but it has a role. Okay, it's a function. It does something, right? Does it help remotely? A little.
You definitely answered my question, so thanks.
So I do have questions in order, but I know that I think Tim said he had to leave at 1 o'clock. So I hope it's all right if I let Tim ask the next question. Tim? Oh, and also one more thing, Barry, I think your audio is on and we're getting some interference. If you want to just be sure that you're on mute. I think you connected with more than one device, so you want to make sure that all your devices are off. Thanks. Tim, go for it.
Yeah, thanks. And yeah, I'm sorry, I do have to leave at 1. So I'm just a bit puzzled about the general issues that are being, I mean, I don't have a really good grasp of what they are. As people may know, my own view is to say, I think that there's a quantum state. I think it's part of the fundamental ontology. Because it's part of the fundamental ontology, I can't analyze it or reduce it to anything else. That's what it is to be fundamental. And how do I understand such a thing? Well, I can talk about the number of its degrees of freedom. I can talk about the space of states it could occupy. I can talk about how its state has an influence on the states of other things. And that's the way I kind of come to understand it. I would give as an analogy when fields were first introduced, and I just would like I have 3 quick points. Take the case when fields were introduced. Okay, so they were a novel suggestion for physical ontology. Are they material? Well, go back to when they were introduced. I don't even know how you answer that. They weren't like Democritean atoms, right? If that's what you thought of as material, they're not material. After a while, we get used to them and think of electric and magnetic fields, and people would probably say they are material. I don't even know what's at issue there, calling something material. So that's why it's hard for me to get engaged in the debate. Is this material? I personally wouldn't call a quantum state material, but I don't know quite what hangs on it. So that's the first question, if you can clarify what's at issue there. A second question is, you said of the wave function, it's part of a law and an ingredient of a law. And if that's to give me enlightenment, I mean, people already have issues about the natures of laws, but beyond that, you now have to explain what it is to be a part of a law, or to be an ingredient of a law, or what ingredients go into making up laws. If I don't understand that, then telling me it's a part of a law or an ingredient of a law doesn't really forward my understanding of it. So if you can give some comments about those locutions. And the third question was, you said at some point it has an explanatory rather than a representational role. And I kind of don't understand how that can be, because it seems to me that things that are explanatory have to have a representational role. I mean, if I appeal to a magnetic field to explain why a particle just got deflected, it's only a good explanation because there are magnetic fields, right? That it represents some part of reality. So if something doesn't represent any part of reality, I don't understand how it can play any explanatory role. So I guess those, if you can just comment on any of those, it would be helpful just to get my feet on the ground into what exactly the debates are here. So I'm still a little lost in it.
Okay. So regarding what's at issue, so the question is, what do you mean when you say, oh, is this material, is not material? So think about the fields, right? I mean, they're material? What are you talking about? Well, I mean, it's a suggestion. When you go back to history, what happened was that at the beginning, they weren't considered material at all. They were physical. They were considered bookkeeping devices. And only after Faraday and Maxwell, all these kind of people, then, and there is a conservation of energy associated to the fields. Okay, so fields, now they're part of the furniture of the word. Okay, so shouldn't we think about in the same way of the wave function? Is that the question? Shouldn't we think of that part of the ontology anyway, even if what is this? So here's this analogy that I see. So people were very strongly, I think, of course, I'm kind of read their mind, but I think they were very strongly inclined to think of the fields as material, also because they give them an insight about what the nature of light was. So material is not the best possible word to use, but maybe just say physical may help at some point after the fields were considered not anymore bookkeeping devices, but something in the furniture of the word. People started to say, okay, so there are two things physically in the word, matter and light, and the fields were what light is made of. Okay, so now I cannot use, in electrodynamics, I cannot use the word material anymore because of course there is matter and there is light, okay? But if I use physical, then you can see matter is made of particles in classical electrodynamics and light is made of waves, electromagnetic waves of the fields. So in the case of the wave function, it's not like that. There is a disanalogy in that. The disanalogy is that there seems to be no energy associated with the wave function. There seems no physical thing associated with that. So while fields we were trying to explain what light is. In the case of the wave function, we are not trying to explain anything else. So that's where I see this analogy to be. So that's where I think that there is a question which is different from electrodynamics. And that's why I think people were interested to analyze exactly what the wave function is, are driven into that. And that's why people are just kind of, yeah, I know that you want to say that the quantum state is not, is primitive, and therefore I don't need to analyze it anymore because it's just part of what there is. So that's why I think that people that's why I am unhappy with that, because I don't see the strong analogy with electrodynamics as much, okay? So regarding the second comment, regarding what do you mean by saying it's an ingredient in the laws? Well, write down any law. You can write down the law of evolution, any Hamiltonian or whatever. You will find pieces, okay? You will find the masses, the fields, you will find the charges, you will find the potentials, okay? They are ingredients in the law. Okay, and the wave function is one of them. Okay, there is a potential. Okay, the potential is objectively something, right? It doesn't depend on knowledge, doesn't depend on anything. It's objective. That's what it is. The wave function, if there is something that I can find closeness in the word, that's where that's what I personally the wave function. That's what I personally think the wave function looks most like.
Can I just?
So that's what I mean, ingredient in the law.
So can I just ask you a real quick question here? Take Bohmian mechanics.
Yeah.
Bohm originally formulated in terms of the quantum potential. And then you kind of can reformulate it using the guidance equation that doesn't mention the quantum potential.
Good.
So when you say something's an ingredient in the law, many people might say, look, these are fundamentally different presentations of the same law, but by your standard of what a part of a law is, in one presentation, the quantum potential is part of it, in the other presentation, it isn't. So yeah. Are you going to want to make an ontological distinction there that depending on which way you write it down, you're presenting different ontological possibilities?
No, not at all. As there is no difference between V and V plus a constant. I mean, sometimes I can write down the quantum potential, sometimes I cannot, or I don't want to. Sometimes I'm just going to use the density matrices. Sometimes I'm just going to use psi. Sometimes I'm just going to use psi, e to the I, whatever. It doesn't matter. It's part of the law, whatever, it is part of the law as, and then of course you're just going to say, yeah, okay, right. But what about the masses? You mentioned the masses. Yeah, okay. The masses are constant. They are what they are. Okay, that's another conversation to be had. But what I wanted to say, so regardless of the way in which I write down the law has some kind of information encoded into that is translated back in the way in which it acts on what matter is in the word. And so if you have an entity that translates the very same information as the one that you're considering now, that doesn't make much of a difference. I don't want to make an ontological distinction at all. And so regarding the explanatory rule, so I think you said, how
can it be?
How can something be
not representational?
Right.
How can you appeal something to explain a physical phenomenon if it doesn't somehow represent something physical?
Yeah, I mean, go back to electrodynamics at the very beginning, in which people considered the fields as just bookkeeping devices. They were thinking they were explaining stuff. Okay, so that's a way in which you can think of that. So if you think the fields aren't real, as people at the beginning thought, they really at the beginning thought that everything that exists is just the particles, and the fields are just one way to write down the force. Okay, well, we don't like for action at the distance, so we introduce the fields, right? They're helpful. Okay, they're explanatory. Okay, that's part of the way in which we account for the motion of matter. Okay, so that's one way to go. But of course, maybe what, I mean, maybe we should talk more about what explanation is supposed to be, which of course I agree on.
Okay, we have just 2 minutes before the next talk. Dave Baker was, oh, can people not hear me?
No, I wasn't hearing Tim. I saw Tim that was talking, and then
I'm sorry.
Oh, he needs to
Tim,
go.
did you have,
Okay,
you have to go. Yeah, bye, Tim. So we have just 2 minutes for the next talk. Dave was next on my list. Dave, do you have a quick question, or do you want to wait until our open discussion at 3?
I would hope it could be answered somewhat quickly, but it's along similar lines to Alyssa's question. So normally functional, like functionalism, you know, you're not seen as having a complete theory of the subject matter unless you have a theory of what the functional realizers are, in addition to a theory of what their functional, you know, like role is. So like, what are the realizers in this case? I guess would be the question.
Okay, yeah, so I think that, yeah, no, so I think I need to distinguish myself from what's going on in the philosophy of mind much more than I just did. Yeah, so I don't have anything more enlightening to say other than thank you. This is exactly what I need to think about.
Great. Thanks so much, Valia.
No, thank you, guys.
David, are you ready to go?
Yeah, I probably need about 2 minutes to turn around and touch base with people. So if you don't mind giving a 2-minute break, that'd be helpful.
Oh, sure. That's not a problem at all. Why don't we all take a 2-minute break? Okay, great.